wide lecture. Oh, okay, sorry. So we'll talk about a lot of topics, maybe not too deep, but this will give you a broad understanding of the field. So how many of you know what ChatGPT and OpenAI is? Just put a plus here. I'm one of those people. Maybe you are as well. Okay. Okay, wow. Yeah, they made some noise over the internet over the course of the last few weeks. So when I was working on something just a couple of weeks ago, I wanted to get myself a machine on Amazon AWS with a bunch of GPUs in it. So I wanted to use like NVIDIA toolkits. I wanted like to run AI on the GPUs. And generally people do this kind of stuff in Python. But the reality is that today the demand for like AI and the GPU access is so freaking high that it was impossible for me to get any machines in a matter of a couple of weeks. So even though we work a lot with Amazon AWS, nowhere in the United States and nowhere in Europe there was a single machine available on demand equipped with GPUs for me to work on it. So why I'm telling you this is just to emphasize how important efficiency is in software. So because those neural networks are so big and so inefficient, that even like the largest cloud provider on the planet didn't have enough capacity to sustain the demand. Today, we'll be talking about the simplicity of Python and the efficiency of assembly. In my company at Unum, we actually use both of those languages, or I should say families of languages. So Python 3 is very common at Unum, but we also do assembly for x86 and for ARM. We also use SIMD intrinsics on NVIDIA GPUs. And aside from this, we do a lot of C++ and CUDA development. So if you are new to like C++ or assembly, don't worry, we'll not be diving into the nitty-gritties, but we'll just know enough to understand which kind of libraries to use in our everyday work so that our programs run fast and scale linearly or like ideally sublinearly. So how many of you know C++? Just put a plus. I think I'll be one of those. Two. Okay, so it's three, four. Okay, we have some people, maybe like less than half of participants. Let's start with a library that has nothing to do with C++. It's called Beautiful Soup. The name is a bit confusing. If I only knew the name, I wouldn't know what the library is doing. So this is one of the most commonly used libraries for internet scraping. Whenever you walk through internet and maybe scroll through pages like this, what you see is a rendered HTML page. The problem with Beautiful Soup is that even though it's super easy to use, you can just import the library, then build up your soup, which is just a parsed version of the HTML page, and then immediately print the tree, the hypertext markup language tree. This library is super slow. A few years ago, when I started building Unum, I started building the frameworks behind Unum. One of the core things I was doing on weekends, I would take a simple Python library and I would try to rewrite it in C++. So just keeping the interface as simple as here, like dot prettify, or let's say dot I, dot find. But the same thing in C++ would work maybe 50 to 70 times faster, at the very least, on a single core. And then one of the benefits of C++, or let's say assembly, is that you get like full control over parallelism, garbage collection. So one of the problems that I constantly face with Python is that I have to work against global interpreter lock. This is the mechanism that kind of controls the access to certain variables within Python runtime. What it essentially means for you, the developer, is that if you want to have multi-threading in Python, you cannot really get it. So like you want to have like multiple cores on your server and every one of the cores is working on a separate part of the problem. So let's say you want to accumulate 1 million or let's say 1 billion numbers. In C++, it's very easy to kind of split those 1 billion numbers into 10 chunks for 10 different cores, and every core will be analyzing its own part. In Python, this is very tricky. In Python, you cannot do like multi-threading when different cores are working on different parts of the same problem. What you generally do is multiprocessing. This is kind of a version where different cores are working on different parts of that problem, but they cannot do it in the same address space. So this sounds already a bit technical. Let's look at the examples of libraries that kind of rely on those mechanisms, such as like using both Python and C++ to deliver high performance. And we'll go directly to machine learning libraries. So this is PyTorch. Just raise your hands if you know what PyTorch is. Have you ever used it? Oh, let's do the opposite. Put a plus if you've never used PyTorch. Seems like everyone has used it. Oh, okay, we have like 4 people who have never used it. So PyTorch has 64,000 stars on GitHub. This is one of the most popular libraries in the world. It's implemented mostly like half and half in C++ and Python. So C++ together with CUDA is responsible for about 49.8% of the source code. Together with C, it's even more than that. And then Python is 44%. This is very representative of almost all high-performance computing libraries today. So you want to make your library as simple as possible for Python users to benefit from it, or for you to be able to experiment with this library in different scenarios. But because the underlying number crunching is so complicated to implement in Python, even with just-in-time compilation, people rely on the library to be implemented in C++ and then wrapped in higher levels into something usable in Python. So within PyTorch, if you go through their manuals, almost all of the manuals will be in Python. But in reality, almost every part of this library is written in C++, and you can work with it directly in C++. The problem is that most do not really have time to experiment with the low-level languages like C++. So what happened is democratization of the industry. So people started shifting to libraries that are much simpler. So in Python, there's generally like 2 or 3 libraries that everyone knows. One of them is NumPy, which is essentially part of Python ecosystem already. The second one is Pandas. It's very common among data scientists, but it's not default built in into Python. And then the third one that I like is called Network X. This one, the last one, is used for things like graph theory and network science. Pandas, NumPy, and Network X are like the bread and butter of every data scientist, of everyone who uses Python. Still, those 3 libraries were originally implemented in Python. And over the course of the last couple of years, I've been giving a lot of talks on how people should replace those libraries with alternative tools. One of the best of those alternative tools is what's called Rapids. Rapids is built by NVIDIA. So being a big company, they can actually allow themselves to build a lot of software that is just supplementary to the hardware that they produce. And what they designed is a library that is very similar to, let's say, Pandas, but is accelerated on the GPUs. So for you as a user, there is no difference between, let's say, typing import Pandas SPD like this, or import QDF SPD. So what's happening is, regardless of like which version you're using, your source code isn't changing much. You are still using the same application. But if there is a GPU installed in your machine and you use the QDF version, sorry, I misspelled it, QFF like this. Yes, sorry, we have a question. I'm listening. Okay, no question. But if you use QDF, your source code can easily be 10 to 15 to 20 times faster. You see here, the speed up is 16 times. Then on mergers, 53 times faster than Pandas. Counting unique values would be 72 times faster. And then group by is one of the hardest operations in business intelligence. It is 78 times faster. But there is a catch. So whenever NVIDIA is working on something, they are targeting their own GPUs. So in a computer, you generally have 3 primary tiers of memory. The first one is RAM, random access memory. This is where most of your applications live and work. The second tier would be VRAM, video random access memory. So this is the memory that is tied to your GPU, where the data is stored available to this GPU. VRAM is generally a lot smaller than RAM. So on super high-end servers on which most people do AI, you can have, let's say, 1.5 terabyte of RAM on a single machine, but you only have 80 gigabytes of VRAM on a single GPU. This is max. You cannot get more than that at this point. So you can only apply QDF and get those 72x performance improvements if you're working on something that fits into video or random access memory. So this kind of limits your addressable memory by a factor of 20 compared to what you could do with pandas. Doesn't sound very cool, but there is a solution. So just a couple of days ago, there was a major release, Pandas 2.0. One of the core ideas of Pandas 2.0 is to adopt what is called Apache Arrow. Apache Arrow is a columnar in-memory format. Its idea is to implement tables or arrays in C or C++ and have this interchangeable format between different languages. So let's say I'm using Ruby, or let's say I'm using Golang, or maybe I'm using Java, which I hope I won't. But still, if I'm using any one of those languages, every one of them has their own representation of an array. It has their own classes, their own object-oriented programming abstractions. But what if I want to design systems that combine different programming languages and different libraries written in different programming languages to analyze the same data set? So what would happen oftentimes is that if I'm using Python on one side, and then there is another team that is using Rust, I will have to convert the data from one format that is common to Python into a format that is common to Rust, and then vice versa. So if two teams want to exchange their results, they will be doing conversions back and forth all the time. This is super expensive. If you're doing lightweight computations, such as just accumulating the number of entries in a specific column, or like unique entries, or just grouping them by a certain value, and every time you do this, you have to convert to another programming language abstraction, you will just waste most of your time doing those conversions rather than the computation that you want to do. So this project came along a couple of years ago. It is a foundation. So it's not just a single project or a single company that's behind it. This is like a standard that the industry decided to follow. The idea being is that there is this library called PyTorch, which people use for AI, machine learning, and even tabular machine learning. Then there is Pandas, where people do business intelligence. There is Rapids that people love and enjoy for GPU acceleration. But there is a problem that whenever you want to exchange information between those packages, you need to convert them. Now you don't, because Apache Arrow is already supported by every single major framework out there. So what you can do, even today in Python, you can accomplish essentially like maybe 70-80% of throughput available on any device. Like if your CPU says it can crunch this many numbers a second, you can reach this level with some framework, and then you can switch to GPU, use another framework that is more optimized for GPU, and do this through Arrow. So a few months ago, we've done this comparison on our website where we talk about frameworks for tabular processing, for numerics, and this kind of stuff. So we compared NumPy and QPy. They do not really rely on pandas this much, but there's also another blog entry. Let me find it. Billion rows, pandas, QDF, Modin, Arrow, and Spark. And this is not an exhaustive list. So all those packages, pandas, QDF, Modin, Arrow, and Spark, kind of do the same thing, more or less. They're just implemented in different languages. And here we showcase how different the performance of various packages can be. Sometimes, compared to pandas, we get a 15-time performance improvement when we use QDF. So the problem being that this whole data set is about 40 gigabytes, and our GPUs didn't have this much memory. We used something smaller than A100. So we had to slice the entire data set into multiple parts and exchange that data set. Still, this is a very manageable pipeline that you can use to achieve maximum performance. So now, when we've kind of covered the technicalities, the mechanics of like how this world is being organized, like there's a lot of players, there is a shared interchange format. Let's talk about the businesses and the companies and the higher level products that you can combine together. So one of the famous examples, even though it's not super relevant for this specific conversation or like Panda specifically, Python specifically, there's this Apache Kafka, which is one of the most famous streaming services or like message passing services. They're written in Java. They're pretty slow. They rely on outdated technologies. And a couple of years ago, another project called Red Panda came along, and they proposed something that is 10 times faster, has 6 times lower ownership costs, doesn't rely on Java virtual machines, so it makes it much more portable, and people just loved it. So this kind of showcases that the industry is ready for change if you can offer a valuable alternative, something that has higher performance, but is still equally usable. So in case of Red Panda, they are fully compatible with Apache Kafka API, similar to how QDF is fully compatible with Pandas. So bearing this in mind, there is something I want to show you that I've been working on for the last couple of years. So Unum, I started 7.5 years ago. This is not my first company. I've had a few of them many, many years ago. But in the past, I would work on product level stuff. Now I don't. Now I just work exclusively on infrastructure. Why is this a good news for you? Just because you can take the infrastructure that I build and then use it for all kinds of pet projects or products that you want to build in the future. And my goal is to make the infrastructure so fast and so efficient, then the products or the ideas that you have in your mind will scale beyond the products that your competitors build. On this path, with our team in Armenia, or actually 2 teams in Armenia, we've built a bunch of cool libraries. About 90% of them are closed source for now, but we are unrolling them one by one. So I invite everyone to go to our GitHub. And as we're all doing this online, it's easy. But before we do, I see there's a question from Anush, which one is better, QPy or Numba? Thank you. Thank you too, Anush. So they're kind of a bit different. QPy is exclusively for GPUs. Numba started by focusing on JIT compilation for CPUs. I guess they may have a backend for GPUs. This may not be their primary objective. So if I'm targeting NVIDIA GPUs, I'm still using QPy essentially any time of the day. But there's also other JITting libraries. I think there's a case when I used Numba a couple of days ago for JIT compilation of my Python scripts. So on our website, for example, we have this beautiful artwork like this, or like this, or like this. Believe it or not, I drew it, but I used computational methods for this. So I defined a differential equation in Python, but because Python is very slow for numerics, I used the JIT compiler for it. So the way I can find it is like this, funky attractors, and here we go. So there's this library that I've worked from Pierre's Segon, actually one of the best libraries I've seen, but with 0 stars on GitHub, which is remarkably shameful. And the way it looks like is like this. Oh, in case my internet loads, I'll be able to show it. Okay, so we take Numba, we import the JIT compiler from it, and then we just define the differential equation. In this case, this is the Clifford's strange attractor. There is an alternative De Jong. I can actually share the link here if you ever want to try to draw this kind of art yourself. Be my guest. But still, let's go back to the conversation. But if you have any questions, don't hesitate. Just write them down in the meeting chat. I'll be happy to answer. So about 90% of the libraries that we write are closed source, but we are open sourcing them one by one. And the first library that I've open sourced last year is called Universal Keys and Values. The second one that we've open sourced just a few weeks ago was called Q4. This one is built purely in Python. UKV was built in C++, but has amazing Python bindings. And then UJRPC was just released a week ago. In a single week, it gained 634 stars on GitHub. So it's like a super popular project. Actually, all of them have been trending recently. Let me share them with you. I'd be actually very thankful if you ever find them useful or just can put a star on them. This would help us grow the projects and attract more people so that we are kind of motivated to share more with the community. So let me just tell you what kind of libraries we're building and what's the idea behind it. So Kafka and Red Panda are doing streaming. UDF and Pandas and Numba and CubeY, they're doing pure numerics. But there is a lot more in the world than just that. And some of the pieces of modern infrastructure are even slower than those. So there is high-speed networking, but storage is still very slow. So we started our company by designing the fastest database engine out there. So we have our own in-house database engine, which is called UDisk. It's a proprietary key value store. But on top of this key value store, we've built up a database. So this project, UKB, is actually our approach to building databases. How many of you know Redis? Just put a plus. Zero? Okay, how many, or put a minus if you don't know Redis. Heard about it, never used? Okay, some minuses. So Redis is an Israeli startup. They are actually one of the highest valued startups in the country. What they've designed is essentially a hash table or like an in-memory associative container. The idea being that this is essentially like Python dictionary, like this, but it's available over the. So what you can do, you can have like this shared dictionary. It runs on a single server, and then many different machines or many different programs can talk to the same dictionary, add entries into it or remove entries from it. But the way you do it, you are not doing it through Python. You are doing it through special operations. In their case, the operations may have name ping, hsat, sat, and then you provide the key that will be used in the dictionary and the value. You can ask you can request the operation called incr by float, which is obviously increment by float, that will take the key E, will increment it by 0.43, and it will get the result 3.14. So this is kind of the domain-specific language that Redis provides for its customers as the interface. One of the unique, interesting things that they've built that is very unusual for the databases ecosystem is they've crammed multiple databases into the same product. So they have this thing called Redis Stack. It's essentially an approach to build multiple database products within single thing. So it has a part called Redis JSON. So if the key is still E, but the value is not 2.71, but instead a JSON document, you can use this alternative interface called Redis JSON to talk to Redis as if it's a document database that stores JSON files. And then there is Redis Search, which is essentially a competitor to Elasticsearch, a thing that does full text search queries on whatever data you're storing inside. And then there is Redis Graph, which is essentially a competitor of Neo4j, a graph database. Why this is so unusual? Because most of the database companies, they kind of differentiate from someone else that we are not going to be like a database company for everything. We are going to be a database company for documents, or we are going to be a specialized database company for graphs. We thought we can do better. So we've unveiled something really unusual. But before I show you what we did, and this is very similar to Redis, I want to show you one of my articles. It's called 2021 in database companies called Gold Rush. So it just so happened that many, many years ago, I was investing into tech companies. And I was an investor in MongoDB, in Elasticsearch, and in Snowflake. Those three companies are some of the most successful IPOs of the last few years. So MongoDB at some point, at the moment of writing this article, was valued at $36 billion. This by itself is about 10 times larger than the government budget of Armenia. Elastic is $11 billion. Snowflake is $104 billion. And those are new modern companies. This is not Oracle. Oracle existed for 40 years. It's no wonder Oracle is so big. But those companies, the demand for their services and for the kinds of databases that they design is so high that the companies are valued in as high as $100 billion. Because there is like this shift in the industry, people start researching alternative databases as well. So within just a single year, this entire list of companies have raised absolutely absurd amount of money. Like Databricks raised $2.6 billion in 1 year. Cockroach is 438 million. Neo4j is 392 million, being the total 582 million over the history of the company. So if you're thinking that this is a lot of money, you are definitely right. But one of the things that kind of surprised me as well is that there is not too much tech in those companies most of the time. So we thought for ourselves that we can replace all of those companies in a similar way that Redis does. So for Redis, instead of designing 10 different database companies, they designed one core key value store. And on top of this key value store, they added specialized functionality for graphs, for documents, and for search. We did the same thing and we open sourced it. This is precisely the project UKV. So what UKV does, it essentially takes any underlying key value store, which can be our proprietary key value store. It can be Redis or any other solution from Facebook or Google. And on top of it, it adds functionality to store binary data, to store graphs, to store documents, to store texts, or even vectors. So only part of this functionality has been implemented so far, but it's already enough to have like a super competitive solution. But Ash, you are probably asking yourself, Ash, why are you talking about databases? We're talking about Python here. Well, look here. Remember, I told you that Redis is like essentially a dictionary. Our database is similar. So if you just imagine that instead of this embedded.database, you write dictionary, this second line looks super familiar. So we take the main collection of the database, we put the key 42, and with the value is high. And the cool part is that because this is not just a single database project, this is like an ecosystem project, you can actually replace the imported part the same way as you can type import pandas or import QDF, same way you can type import ukv.umam or import ukv.rocksdb or import.flight client. And the only thing that is changing is essentially where the final data will be stored. So your application doesn't have to change. This line, db.main 42 equals high, will be the same for both this variant and this variant. The only thing that is changing is how you initialize this container. That's it. So for you to build up a stateful database-based application, the only thing that you need to do is pip install UKV, as simple as this. And you will have one of the fastest databases on earth ever designed, available to you through simplest Python interface, very similar to the most obvious native things, and you don't even have to use custom languages like with Redis or like SQL or something else. And as we're there, let's just also look into this. So if some of you are familiar with Network X, this will also immediately look familiar. So Network X is the super popular library for network science. Essentially, when you have a lot of vertices, a lot of edges between them, and you want to analyze the communities, how clustered people are together, how much they talk to each other, or how dense the transportational network is, what is the shortest path from one point to another. But if you're using something like Network X, it's super slow. It's built purely in Python. It will never work with really large graphs. So if you take just the transportational network of Yerevan and you put it into Network X, it may work. But if you just try to scale to the transportational network that covers, let's say, all of Georgia, all of Armenia, and all of Iran, kind of at least three countries together, Network X will just die. With Unum or with UKV, you can build up graphs with the identical interface to Network X, but you can cover not just a transportational network of one city or one town, you can cover the whole planet. You can add billions of relations between all kinds of objects. And even if they don't fit into memory, if they just fit on your SSDs, this is good enough. This system will still work. Okay, we have one more question. What are the performance differences between using third-party DB engines versus UMAM? Okay, in reality, there is a huge performance difference. So there are two database engines that we maintain. One is called UMAM, and the second one is called UDisk. UDisk is proprietary, and UMAM is open source, but UMAM is super simple. It's just an in-memory hash table. It's essentially as simple as Redis. And then there is RocksDB, which is the second best database engine on the market after hours. It's built by Facebook. And then there's LevelDB by Google. So UDisk is about 5 to 7 times faster than RocksDB. This is the performance penalty that you should expect. This is how much faster we are. I hope this answers your question, Arman. So, okay, this project by itself is already like super ambitious, but you may be asking like, Ashot, okay, you have 5 more repositories mentioned on Unum, Unum's GitHub. What are they doing? Let's dive in. Oh, okay, diving in, I've closed the chat, sorry. Give me a sec. Okay, I'm back. So the second repository that we've released is called U4. This is actually kind of interesting. It's all about AI. What it says, unified form is a multimodal inference library for semantic search applications. Or in other words, it's a multimodal neural networks library for semantic search based on mid-fusion vision language transformers. Sounds very fancy, but you don't need a PhD to understand what it does. So the idea is that in modern machine learning, there is a concept of embeddings. An embedding is essentially a vector representation of whatever data you're working with. So over the course of the last few months, we've seen OpenAI DALL-E and OpenAI Clip. OpenAI Clip is the predecessor of OpenAI DALL-E. DALL-E is the text-to-image neural network. But this neural network that generates images from texts is based on a neural network that understands the similarity between a text and an image. And we have our alternative to what OpenAI does. It's called UForm. Essentially, the core idea of the library is that you have to learn how to compare texts and images by their meanings. So let's say you have an image on which a dog is presented. And then you have a text which says, a dog is sitting on the grass. This library has to be able to tell you that the textual part and the image are identical. But if you take a picture of a cat and use the same textual query, if this neural network works as good as I'm describing, then it should say, no, Ashot, those images and texts are not identical, and you should try some other query. So almost all search companies are built on this technology. Bing, Yandex, Google, Baidu, DuckDuckGo, anything else, anything you think about, any kind of semantic search is built on this kind of technology. So this is why it's such a big deal. And to use it, you don't need much. You only need to import UForm, then you type in UForm get model, and you describe what kind of neural network out of the ones that we've already prepackaged you want to use. And then it's just simple as this example. It's essentially just 7 lines of code, pre-process the image, encode the image, and then you may want to be able to compare those two. So at this point, our library supports English, German, Spanish, Turkish, French, Italian, Japanese, Chinese, Korean, Polish, and Russian. There is no support for Armenian yet, but if you're enthusiasts like us, I'm inviting everyone to try and contribute. Maybe it's just like participate in training experiments or maybe get an internship at Unum. There are already waits for the English version and the multilingual part. But aside from being more accurate than most of those other models for search applications, we're also super efficient. This is truly important for us. So one of the things that you can do with UForm, you can take video input from hundreds of cameras and route this video input from many, many cameras into the same GPU. And the same neural network will be analyzing frame by frame every video line concurrently. So the model that everyone else uses these days, let's say for textual part, BERT-based uncased, processes 1,500 sequences per second. Our neural network baseline does 6,809. So this is about 4 or 5x performance improvement, but we are just talking about the open source deployment part. We also have a version of this that we're preparing for the cloud launch. Let me just show it here. It's called Uniform. It's more letters, so it's more fancy and it's supposed to work better than uniform. So our current numbers for this uniform thing is not even 6,800, but closer to 25,000 sequences per second. So on one side, you can use something like BERT based on case, which is 1,600 operations per second, or you can use ours, which on the same hardware will provide 15 times more performance or more speed, but with the same accuracy at the same time, which is kind of absurd. So this is the second one. I actually love writing, and I generally try to teach our kids within our teams to write as well. The best portal where I share my work is Hacker News. Can you just put a plus or minus if you've ever heard about Hacker News or you read about it? Arman, well done. What about the others? For those who haven't seen Hacker News, this is this website. It looks super old, like as if it comes directly from 80s, but this is actually my favorite website. I check it out almost every night or every day, looking for news on interesting or weird tech. And if you can write something that's supported by the Hacker News community and loved and discussed, this is generally a very good marker of quality content. I was very lucky a few times to be featured on Hacker News. The last two articles I've released in the last 2 weeks, I've just shared the link with you for our Hacker News posts. One of them was called this, beating OpenAI clip with 100 times less data and compute. So OpenAI has had $1 billion in funding. And then they got another $10 billion from Microsoft. They have about 400 of the brightest researchers on Earth working on some of the most expensive hardware available to anyone. So it's a total of $11 billion of assets and 400 exceptionally bright people. But the very fact that Unum, and not even the whole Unum, but just 2 people on our team are capable of competing with them, with our tiny cluster on one of the core applications being search in terms of accuracy and performance is mind-boggling. So obviously this article made a lot of fuss. I was in Stanford when this aired. So we had like a lot of heated and interesting discussions with other kids at the university about how this is possible. But if you go through our documentation, you will understand a lot about this domain. The second thing that we've released is called UJRPC. It's short for uninterrupted JavaScript object notation remote procedure call library. So a lot of words. In short, it's UJRPC. So the idea is that there's this library called FastAPI. It's also written in Python. It's super easy to use, but it is not about performance. Actually, like that was my assumption that they are not about performance. But once I posted this library, someone reached out to me and said, actually, FastAPI claims that they are a modern, fast, high-performance web framework. So they have the claim that they are fast. The question is, how much faster can Unum be? I've already spoiled the question because you know the answer. It's in the title. It's up to 100 times faster than FastAPI. It's equally easy to use. So on the left side, you see the variant that is FastAPI. On our side, it's just as many tokens. Again, we have 2 backends. You can either type in ujrpc.posix or ujrpc.hurang, depending on which machine you are running. So if you are running on a very new Linux, you can import this one. But if you're working on Macintosh or you're working on older Linux, you should use this one, the older version. So I was sitting in Armenia a couple of months ago, and I tried using FastAPI for one of my projects, and it was just remarkable. The latency between performing a call on a web server was about 6 milliseconds actually. So here I'm writing 1.2 milliseconds because this is happening on a much more advanced Linux machine. But on my Macintosh MacBook Pro from 2019 with an 8-core CPU, the latency was 6 milliseconds. For anyone familiar with networking, this sounds ridiculous because if you're sitting in Yerevan, in 6 milliseconds, the signal can reach Georgia and come back. That is a lot of time. So I designed an alternative, but when I was designing the alternative, I already knew we're going to be a lot faster. I just didn't know by how much. So our initial variant, has a latency of 62 microseconds instead of 1.2 milliseconds. Our version for like advanced Linux has a latency of only 22 microseconds, and we are capable of squeezing 231,000 requests per second, while Fast API only did 3,184. So this is kind of the stuff that we do at Unum. We try to build projects that are equally easy to use as the most famous Python projects, but are super fast beneath. And with this, I will wrap up the primary introduction part, and we'll just go directly into questions and answers. Okay, so the first question is, what drives this performance increase? That's a great question, and we have the answer right here. The two main reasons are IO-Uring and SimJSON, and the third one is CPython. Let me explain what those mean. So first of all, what is IO-Uring? IO-Uring is the new interface in the Linux standard. It appeared around the kernel version 5.1. Its idea is that doing system calls on a computer is very expensive. What does it mean? So sometimes your program has to request something from the operating system. So if you're running on Linux, Macintosh, or Windows, your program, Python program, has to talk to the operating system requesting something, maybe more memory to hold your data or something like this, or request data from the SSD, external device, or from socket, send some data over the network. For all of this, you would generally do system calls. But then this IO-Uring thing came along. It's a project that has shaped the storage and networking industry over the course of the last couple of years. There are still very few libraries that support it. We are like one of the exceptions, but if you know how to use it, you can perform queries without performing system calls. So it's essentially a way to request something from the operating system without performing a block or like an interrupt. So an interrupt is essentially a point in time when your thread, a user space thread, like a space in which your program runs, is being interrupted, and then the operating system continues working on the same core. So if you need to preserve some context, switch to another task, and then come back to your application, this is an interrupt. Interrupts are very expensive. So if you can use IO-Uring, you can avoid interrupts. This is one source of the performance. Second source is called SIMD. It's actually one of my favorite topics. So if you go to youtube.com and hear Ashot Vardanian, over the course of the last few years, I've given tons of lectures on what SIMD is. SIMD is single instruction multiple data. This is the kind of assembly instructions that you would want to benefit from in your application, but you cannot do it in Python directly. So this is one of the points of this talk specifically. Like, you can benefit from the optimizations that crazy people like me are writing down in the C and assembly layer without ever having to write them yourself. So essentially what SIMD is a way to request the CPU to perform more than one operation within a single cycle. So you would be thinking, oh, that's parallel computing, obviously. But no, parallel computing in general, or like multi-threading, is when you have multiple cores working on at different points of time. SIMD opens up a single instruction, multiple data. So with the same core, not multiple cores, multiple entries of data will be processed in exactly the same way. So instead of telling it sum A and B, two integers, you can tell it to sum pairwise 8 integers in an array A and 8 integers in an array B. And what will happen if you use those special instructions within a single CPU cycle, just 0.3 nanoseconds, you can get the result back. So this is super fast. You're essentially getting an 8x performance improvement if you're capable of using those. But the last bit that I want to share is the way we write bindings. So even within our projects, we do not always maintain very high or like the highest possible quality standard. So let's open up Python folder of UKV and something like database.cpp. So what you will see here is the way we define Python bindings for C++ project. For this, we use a library that is called PyBind11. It's a C++ library that just makes wrapping anything for Python much easier. But if you go to our library called UGRPC, you will actually find one of the very, very few, maybe a dozen, of projects on internet that uses direct CPython bindings. What it means is that we don't have any additional library that helps us wrap anything for Python. We do this directly. So what we do, we use those special CPython, which is the Python runtime, functions like PyList get item, PyTuple get item, PyObject get attribute string to talk directly to the Python runtime and invoke functions in Python from C++ or vice versa, call C++ functions from Python. And the benefit is that you can have this experience of at server, essentially having decorators and other Python things without major overheads. So if we were to use PyBind11 in this project, we wouldn't have gotten 200,000 operations per second, or even like 79,000 or 40,000 operations per second. It would have been much lower. So I hope this answers your question, Armanjan. Anyone else? You're welcome. In reality,
can I ask one more question? Sorry, I just didn't want to type a long message, so I'll just ask you directly.
Yeah, sure. Okay. And guys, you feel free to enable videos. I'll be happy to see your faces. And we have like this tiny environment here. No need to be formal.
So my question is a bit more general. So a lot of times when we're talking about data science and performance, it's all about circumventing the limitations of the Python language. It seems like we're just stuck with this language. And judging from your presentation today and the presentation you did at CPPCon back in summer, I believe, again about C bindings, a lot of it is, of course, clever engineering, but a lot of it is also, just trying to do it low level and just not, using Python for a lot of these things. The question is, do you think, I was watching this interview with Jeremy Howard, who is the creator of Fast AI, and he was like, we can't keep using Python for much longer. The industry will have to switch to something like Julia or a language that's much more, faster than what Python currently offers. Do you think that will happen anytime soon, or are we just stuck with this one language?
I think we're stuck for now. So the switching cost is way too high. Jeremy Howard was actually one of the supporters of the project called TensorFlow for Swift, or Swift for TensorFlow. So there was a group at Google run by Chris Lutner, who's one of the most celebrated and impressive engineers in the history of computing, or like recent history of computing. So he's the person who designed the LLVM compiler. He's designed the Swift language. He has designed MLIR, which is the intermediate representation language for neural network stuff, essentially like a meta compiler for AI. And this guy has been working on implementing, like essentially re-implementing TensorFlow in Swift. Even with Google's resources and his amazing experience, they couldn't progress far enough to convince the rest of the industry to switch even to this. And Swift is a super easy language to use. Like in some ways, it may even be easier than Python, to be honest. But at this point, I don't see this as like too big of an issue. So we have enough infrastructure implemented, let's say in C++, to continue moving with certain pace. And then Python also keeps evolving. So maybe like modern Python libraries are getting a couple of times faster. Guido van Rossum has returned into the Python project last year. He is promising up to 4x performance improvement over the course of 2 years. Actually, like it's super easy to do. I'm one of the sponsors of the Python runtime and the Python project. If I had more time, I even have like a fork that I could have contributed into like the Python runtime that replaces the global interpreter log. But I'm not doing this because I know the community will be a bit reluctant to accept this contribution. In the last 15 years, there have already been 2 cases of people who kind of circumvented this limitation and had their own forks of CPython runtime implemented without global interpreter log. So at least you can get multi-threading. I'm not saying C speeds or C++ speeds, but at least multi-threading, at least close to linear scaling with more cores. But even that wasn't accepted. Maybe now, once the problem is more pronounced, they will be more open to this, but I don't see too much change. I think this will go forward the way it is.
And good luck with your endeavors.
Sorry? Good luck with the endeavors?
And good luck with the project, yeah.
Anyone else, guys? Any complicated questions on the future of Python or other programming languages? Anything philosophical? Maybe you have any pet projects on your mind, and I'll be happy just to maybe give advice which libraries to use and which ones not to use. Are students at ACA supposed to, let's say, have semester projects or anything like that they need to defend?
Yes, we usually have in professional courses, but I'm not sure. Arman is one of our students actually studying now. I'm not sure who else is from ACA now.
Oh, sure. So if you have any projects like this on your mind, we have our own Discord where we kind of help provide support for like anyone using our libraries. So if you want to put out like an example of what you've built or ask an advice on what kind of libraries to use and how to combine them, never hesitate. Come join us there. Let me just share it here, or I guess there's like news on the Rust channel here. So it's not completely dead. There are some people using it already. Good. Invite people. No expiration limit. We are welcome to anyone, anytime. And I'll just share it here in the chat. Okay, so any more questions? Anyone? I think I've covered most of the material, but I'll just give you a sneak peek. We have like this placeholder of a library. It's called UNSW. It opens up as uncluttered, navigable, small world graphs algorithm for k-approximate nearest neighbors search in high-dimensional spaces and billion-point clouds. So it also sounds very fancy, but again, you don't need a PhD to use it. So it will again have like Python bindings that are super easy to use at the very top. It will be implemented in C, C++, and with some bits of assembly in it, maybe not directly in it, but in some libraries that it uses. It will be open source very soon. if UKV is competing against MongoDB, Neo4j, and Elastic, if UGRPC is competing against gRPC and Fast API, and if UForm is competing against OpenAI Clip and Cohere, then UNSW is competing against Faiz, which is from Facebook, doing the same thing, Scan from Google, and a bunch of startups like Pinecone, Qdrant, Viviet, and many others who are doing exactly the same thing as this library is supposed to do. So with this in mind, I'm again inviting everyone to follow our GitHub to be always ahead of everyone else in terms of the libraries you can use. Thank you very much, guys. I'll just wrap up.